Back in the section 5.1 playlist, we tried this process out of finding the approximate area that was under the curve y equals x squared between x equals 0 and x equals 1. And we used several finite approximations to estimate this area. Now that we have the concept of a Riemann sum, we're going to find the exact area. Now with that in mind, if I wanted to set this up as a definite integral, it would be the definite integral from 0 to 1 of f of x, which is x squared times dx. So with that in mind, first thing we do is set up our expression for delta x. Delta x is defined as b minus a over n, where b and a are referring to the endpoints of your interval. So this would be 1 minus 0 divided by n, or when simplified, simply 1 over n. Our expression for x sub I star will be a plus I times delta x. A is 0, I is your index, and delta x from the previous step is 1 over n. Simplifying this expression, we get I over n. After that, we're going to plug that into the given function. Now the given function was x squared, so I'm going to plug this into x squared. So that'll be I over n, quantity squared, or more simply, I squared over n squared. Then we're going to multiply this by delta x. So that'll be the expression that we just got, I squared over n squared, and we're going to multiply that by delta x, 1 over n, giving us I squared over n cubed. So up until this point, we're simply making some substitutions and performing very elementary algebra. After this however, when we evaluate our summation, this is going to be a little bit new. We'll also need to call back to several of our formulas for summations. So what we have here is a summation where I is the index and n is going to be treated as though it's a constant. Given that n is being treated as a constant, you are allowed to move constant multiples outside of the summation, which is exactly what we do. We have a formula for the summation from I equals 1 to n of I squared, and that formula is the following. That is n times n plus 1 times 2n plus 1 all over 6. Once here, we can do a little bit more algebra. We can cancel 1 factor of n in the numerator with 1 factor of n in the denominator and arrive at n plus 1 times 2n plus 1 over 6n squared. And finally, we're going to take the limit as n goes to infinity of this expression. I mentioned in the previous video this should be a function of only n, and we see that that is the case. So the limit as n goes to infinity of n plus 1 times 2n plus 1 all over 6n squared. The method that you use to evaluate this limit at infinity is completely up to you. What I'm going to do is expand the numerator as much as possible. And then apply L'Hopital's rule a couple times. Differentiating the top with respect to n, we arrive at 4n plus 3. In the denominator, this would be 12n. This still takes the form infinity divided by infinity, so I'm going to apply L'Hopital's rule one more time. Derivative of the top is 4, derivative of the bottom is 12. Reducing this, we get exactly what we had predicted from section 5.1. We get a final answer of an area of 1/3.